Hello, everyone. Welcome once again to our channel, Making Life Easier. And welcome once again to our series on basic mechanics. Kindly subscribe to our channel, like and share, and leave your comments and suggestions at the comment section. Today, we are looking at moment of a force about a point, example 3. Quickly, let's look at our question and how to go about it. The section OABCQ is loaded as shown. If QN has a magnitude of 25 kilonewtons and CP has a magnitude of 30 kilonewtons, determine the moment of the forces about O. Determine the moment of the forces about O. So we are asked to determine the moment about point O. Let's look at how to solve this example. Good. Our diagram is here, and we want to solve this problem. Good. So here you realize that we have two forces. We have from C to P, and we have from Q to N. So it means that if we want to determine the resultant moment at O, we need to first of all work them individually, and then once we are able to get the moment for the two, we can sum them together. We can find the vector sum. So let's start with the first force, which is C to P. But don't forget that this is a 3D object. So we said that anytime you have a 3D object, your moment, you use the vector approach, and your moment is always equal to R cross F. Don't forget this. When you have a 3D object, it's always using the vector approach, and then we said that it's R cross F, where R is the position vector, and then F is the force in the vector form. So here, let's first start with the force in CP. So the force in CP, we can see that the moment will be equal to, let's represent that with moment 1, will be equal to the position vector. The force is applied at C. The force is applied at C. So it means that our position vector will be moving from where we are taking our moment O to where the force is applied, which is C. So our position vector is going to be R, C, when we are starting from O. Take note of that. It is always from where we are taking our moment to where the force has been applied. Good. So RCO cross our force in the vector form. So our force will be for CP. Good. So having been able to do that, let us look at how to find our position vector. Our position vector, which is RC/O. So to find this, it means that we are moving from O to where the force has been applied. So if you want to know the distance from O to C, we move along this figure here. So you can see that we move this way. Look at the direction. Don't forget that we have stated that our unit vectors are always pointing this direction. On the Y, once we are moving up, it is positive. On the X, when we are going this direction, it's also positive. And on the Z, when we are moving this direction, it's positive. So now you can see that from O to C, we are going to move this direction, which means that we are following the positive side of Z. So our distance there on the Z is 2.5, and it's going to be positive. So we have 2.5 A. And then from there, we move down. And you can see that this is on the Y-axis. This is on the Y-axis, and we are moving down. We said that on the Y, if we are moving up, it's positive. But here we are moving down, so it's going to be negative. So we are going to get negative negative 3J for Y. And then from here, we'll be moving towards this direction to C. And this direction, we said that if X, this is in X axis. So X axis, we said that anytime you are moving to the right, it's going to be positive. If moving from this to that point is to the right, and therefore our S will be positive 4.5 I. We have been able to determine our position vector. So now let's now try to determine our force in the vector form, which we said that is the force in the scalar form times lambda. And we said that lambda is always lambda. We have explained in our previous video that it can be obtained from angles, which in that case it will be cos theta xi plus cos theta yj plus cos theta zk. Or it can be obtained from distances, which will be the vector form, or dxi plus dyj plus dzk all over d. And we also said that it can be obtained using forces. But in this force here, the force from C to P, you can see that we're not giving the distances. We have been given the direction of the force in angles. We have been given the direction of the force in angles. So it means that in this case, we are going to use this formula here to determine our direction cosine. And you can see that here, this force is telling us that this force is only resolved in the Y and in the Z axis. The force is only resolved. You can see that here, this is our Y axis, and this is our Z axis. So it is telling us that this force is only resolved in the Z and in the Y, and they will move in this direction. So we are told that the angle here is 30. The angle the force is making with the Z axis is 30. So we can say that our cos theta zk is 30 degrees. So lambda, we are going to get cos theta zk as cos 30 degrees. So this is our K. But look at the direction. We are moving this direction. We said that our Z should always move this direction. But now, with regards to this force, if you want to get this to this point, if you want to get to the end point of the force, it means that you'll be moving this way. Like this. And it will be in the opposite direction with our Z axis. So our angle is going to be negative. And then this is our Y. On our Y, we are moving up. And we said that Y, if you are moving up, is going to be positive. And if this is 30, we know that this one is making an angle of 90. If this is 30, then this angle here will be 60. So the angle the force makes with the Y axis is going to be 60 degrees. So that is going to give us cos, but we said that it's moving up, so it will be positive. We are going to get cos 60D. So we have gotten a lambda. So this will give us lambda equals 0.5 G minus 0.866 K. And once you have gotten that, we can get our force in the vector form, because our force in the vector form is always equal to the scalar force times lambda. So here we are going to get, we know our scalar form is giving us, we are told that CP is 30. So we are going to get 30 into bracket 0.5 G minus 0.866 K. And from here, our force in the vector form will be equal to 15 G minus 25.98 K. Good. So from here, we can determine our moment. Our moment is the position vector C/O cross our force. So we said that it's good to use the matrix method. So I, J, K. Here for the position vector, this for our position vector. So we can write 4.5 for I, negative 3 for J, 2.5 for K. And our force is here. We only have J and K components. So S component will be 0. our G component will be 15 and our Z component will be negative 25.98. But don't forget that we have already stated that when you are determining the determinant, this one is plus, minus, plus. So if you want to get the I component, we have already explained that you take away all the I components, and then you'll be left with the J and the K, and you find the determinant. So this times this minus this times that. So we are going to get it as negative 3 times 25, negative 25.98 minus 2.5 times 1.5 times 1.5 I. This will give us our I component. Then minus this minus here for our J should be there. So minus our J component, we take away everything in the J section and be left with the I and the K. So this, what is here times this minus this times that. So we are going to get 25.98 times 4.5 minus 2.5 times 0G plus now our Z. So it means that for Z component, we take away everything which is in the Z, and we'll be left with this times this and then this times that. So we are going to get 4.5 times 15 minus negative 3 times 0. And this will give us our key component of the force. And from here, our moment will be equal to, from that computation, our moment will be equal to 40.44 I minus, into bracket, negative 116.91 G plus 67.5 P. And from here, we can just simplify this and say that our moment for our moment 1, which is for CP, is equal to 40.44 I plus 116.91 G plus 67.5 K. And from here, we have been able to determine our moment for force CP. We are left to determining the moment for Kyekyere. So let's look at how to determine that. So for cable Kyekyereernest, that one also, let's represent it with M2. So M2 will be equal to R cross F. R cross F. So first of all, let's determine our position vector. We want to, the position vector now will be from where we are taking our moment O to where K is. Where we are taking our moment to where K is. So to analyze that, it means that we are going to move from point O to point K. And you can see that here, if you want to move from O to K, we are going to move this distance on the Z. And you can see that it is in the direction with our Z axis, our positive axis for Z. So that distance is going to be positive. So since we are moving from O to K, we want to get to K when we are starting from O. We said that we have this in the Z axis, and it is in the same direction with our positive Z. It is going to give us positive 2.5 K. And then we move from this point to that point. We said that on the X, if we are moving from this to that point, this direction is in line with our positive X. So that distance is also going to be positive. We are going to get 4.5 I. 4.5 I. Then once we have been able to obtain that, we are left with our force in the vector form. So our force in the vector form, as usual, is always equal to F lambda. But now you can see that for this instance here, we have been given the force outside our diagram. The force is even outside our diagram. So, but the force is starting from K and then ending at a point here, which is N. we have the coordinates for n, but we do not have the coordinates for p. And from our vectors, we know that lambda is always equal to vector Kyn, since the point of application is Q and the endpoint is n. So vector Kyn over the magnitude of vector Kyn. But here you can see that the point n is outside the diagram. So in this case, we cannot even move around. We cannot move around the diagram to determine the distance which the force makes or the direction of the force. We cannot move around. So but the question has given us the coordinates for n. It means that from our vectors, if we have been given the coordinates of n, then once we get the coordinates of Q, we can be able to obtain our vector Kyn from our vectors. So if we want Kyn, vector Kyn, then from vectors we're told that is the coordinates of the point n the coordinates of the point n minus the coordinates of the point Q. The coordinates of the point Q. So from here, we are able to determine the coordinates. We have already been given the coordinates of n. If we are able to determine the coordinates of Q, then we can be able to determine the distance or the direction from Q to n. So let's look at the coordinates of Q. So or Q. It means that the coordinates of Q, if we want to determine the coordinates of Q, we need to start from point O. We need to start from point O. So if we want to get the coordinates of Q, then now we are going to move from O to Q. You can see that the coordinates of O to Q, we move this distance on the Z. It's in the same direction with our Z axis, our positive Z axis. So it means that we are going to get 2.5 K for our Z, and then we move this direction on the X. We move this direction on the X, which will give us 4.5 I. 4.5 I. So this will be the coordinates for Q. So once you have been able to get the coordinates of Q, then we can use it with the coordinates of n to get the direction of the force from Q to n. So we can say that our Kyn, vector Kyn is equal to, we just subtract the S component of Q from the S component of n, the Y component of Q from the Y component of n, and the Z component of Q from the Z component of n. So here we are going to get our coordinates as 2.5 minus 4.5. This will be I coordinates. The J, we don't have any coordinates for Q, so we are going to get 5 minus 0 for our J. And then for our Z, we are going to get 6 minus 2.5 for K. And from here, we can get our vector Kyn to be equal to, negative 2I plus 5J plus 3.5K plus 3.5K. And from here, we have gotten our vector. We can just determine the magnitude of vector Kyn. And the magnitude of vector Kyn will be equal to the square root of 2 squared plus 5 squared, negative 2 squared plus 5 squared plus 3.5 squared. And from the magnitude of Kyn will be equal to 6.42. And once we have been able to determine this, we can get our lambda. Our lambda will be equal to this over that, vector Kyn over the magnitude of Kyn. And from here, we are going to get negative 2I plus 5J plus 3.5K all over our D, which is 6.42. And from here, our lambda will be equal to negative 0.3i, 31i, 31i plus 0.7 kg plus 0.55k, 0.55k. And from here, once we have been able to determine our lambda, we can determine our force in the vector form. So our force in the vector form will be equal to F lambda, and which will give us 25. Our F in the scalar form is given as 25. So 25 into bracket lambda, which is negative 0.31i plus 0.78j plus 0.55k. And from here, our force will be negative 7.75i plus 19.5j plus 13.75k. So once you have been able to determine our force, then the next thing we need to do is to determine the moment, is to find the moment for that force, is to find the moment for that force. And we said that the moment is the position vector cross our F, which is our force. So let's try to do that quickly, and then we see the results which we are going to get from there. Good. So from here, our moment will be equal to R cross F. And we already have R. Our R is 4.5i plus 2.5k cross our F, which we are having negative 7.75i plus 19.5j plus our K, which is 15.75k. So from here, we said that it is easier to do it in the matrix way. So I, J, and K. Let's put the value there. We have 4.5. We have 0 for here. We don't have any J component. So it's 0, and we have 2.5. And for the force, we have negative 7.75. We have 19.5, and they have 15.75. And this we said plus, minus, plus. So from here, we can say that this will be equal to, if you want to get the I component, we take everything away from I. So you are going to get this times this minus this times that. So from here, we are going to get our components to be 0 times 0 times 0 times, sorry, I think the value for our force here is supposed to be 13. Yes, it's 13. So this is what we have here is 13, not 15. It's 13. And this is also 13. It is also 13. We are going to get 0 times 13.75 minus 2.5 times 19.5. And this will give us our I. And then we do for our G, the minus sign is there, which is up here. The minus which is up is there. Minus into bracket 4.5 times 13.75 minus 2.5 times negative 7.75 J plus 4.5 times 19.5 minus negative 7.75 times 0 for our K components. I'm sure up to now, all of us can be able to do this. So from here, our result for our moment will be 48.75 81.75 I minus 81.25 J, and our K component will be 87.75 K. So once we get here, this is for M2. This is for M2, our second force. And we have already obtained M1 for our first force, M1. So this is moment 2. So M1 for our first force was, I think we had 40.44 J minus, no, this is plus, we had plus 116.91 J plus 67.5 K, right? So from here, our resultant moment is going to be M1 plus M2. We just put the I component for this and that together, the J component of this and that together, the K component of this and that together. And from here, our I component is going to be 40.44 plus 48.75 will be representing our I. And then for our Y component, we are going to get 116.91 minus 81.25. This will be our J component, and then our Z component will be 67.5 plus 87.75 K. Good. So from here, our resultant moment will be equal to 89.19 I plus 35.66 J plus 155.25 K. Yes, that was simple. And I believe each of us have understood the concepts we are applying. If you have any question, any contribution, and any suggestion, we will humbly ask you to write them at the comment section. We'll be happy to address them and also take into account your feedbacks. Once again, thank you for joining us in this video. And we hope you have subscribed and you look forward for our next video. Once again, thank you for watching. Kindly subscribe to our channel and hit the notification bell. Bye-bye.